Alright, so we're going to talk about how to create a little ground explosion using Maya software rendered particles as well as the instancer to create this effect. And so basically what I have inside here is a sphere that's sitting basically at the origin. Let's get this to loop. Animate a quick little point light to just get bright and dim, so we have that little flash in the beginning. And then basically a bunch of particles are emitted from an emitter that's inside the sphere. Those particles then have these pieces of debris instanced onto them. These obviously could be anything. I just took little rocks and put them onto those particles. And then those particles, the ones that are emitted by the first emitter, are themselves emitting particles, which is the smoke trail that they leave behind them. And then that smoke trail is rendered with software rendered particles so that you can get shading and shadowing. So you can see how they're casting shadows on the ground. And so to do something like this, I have the scene open. And so let's look back here. And we can see if I hit play, it's the same thing. And so what we're going to basically do is take this apart and put it back together again so you understand the different steps of what's going on inside here. And so the first thing is let's go in and just get rid of all of the dynamics in this scene. We can see that I've got an emitter, which is at the sphere. That's the emitter that's emitting particle 1. Particle 1 I could just rename debris. And so if I hit play, we can see that particle 1, or debris, is the particle object that has these rocks instanced onto it. Then that particle object is itself an emitter, emitting particle 2, which is the smoke trail. And if we look inside here, we also have some fields. I have a gravity field on the debris, so that when it's emitted out of the emitter, we can see that it goes up, but then eventually falls down with gravity. There's also a turbulence field on those particles, on the debris, just so that they don't all go in perfect arcs. But that turbulence field, we can see, is inside a cube shape, so the turbulence only exists inside this area. Reason being that once these particles sort of exit this area and then sort of hit the ground, I don't want them sort of behaving turbulent anymore, and so I've confined the turbulence to this area. Then the smoke trail particles emitted off of the debris also have a turbulence field on them so that they aren't these perfect arcs either. And so we can see that there is just a little bit of turbulence on those particles. And that's pretty much it. And so let's go in and sort of recreate this so you can see how to do it yourself. So I'm going to delete everything that's related to my particles or dynamics. So I'm going to go and get rid of all the particles, get rid of the instancer node. Let me go and display this display layer here. You can see those are my rocks that I instance. And in Hypershade, I'm going to delete this particle cloud shader because we're going to create a new one. And so now if we look at the scene and I hit play, we can see basically all that's going on inside here is I have a sphere, just a little polysphere, where I animated the visibility. So you can see at frame 1 it's visible, at frame 5 it turns off. And so that's basically just supposed to be the object that's exploding. So animating the visibility on an object that's exploding is one solution. Obviously another solution would be to have a clean version of this object and then a broken version of the object. So at frame 5 I might be switching visibility from the clean version to the broken version, and then the broken version might be dynamic. For example, rigid body dynamic. So inside here, though, for this example, we're just going to have simple animation on visibility on the sphere. And then I've got point lights inside here. So you can see that this point light has its intensity animated. So at frame 1, it's at 0. Then we can see at frame 6, the intensity starts to go up to an intensity of 10. And then the intensity just goes down to 25. So we won't redo that just because that's pretty straightforward. Simple intensity animation. There is another point light inside here, and this point light also has that intensity in there as well. And so that's something where I created sort of one point light to illuminate the ground and one point light to illuminate the particles. So just a couple point lights. I also have a directional light in my scene, just illuminating the ground plane inside here. So if we do a render and just take a look at what we get, we now just have a simple sphere sitting at the origin. It's casting a shadow from my directional light, and these 2 point lights are off. And so first step is we need to create our emitter. So in dynamics mode, create emitter, In the options, I'm going to leave everything at the defaults, create, and move that emitter up here and hit play. And we can see, all right, I'm getting a simple omni emitter. Now, to make those particles a little easier to see, I might decide to go to their display type, go to the particles, and change it from points, let's say, to spheres. So that just makes them easier to see. Even though we're not going to render them as spheres later, we're going to instance some rocks onto them. For now, it makes it easier to see them. And so for those particles that are inside there, off that emitter, the first thing that we might want to do is just rename it and call it debris. So we know that's what that's supposed to be. And then this emitter right here is basically the debris emitter. And so let's just name things debris emitter. Now that emitter is obviously going to be located basically down here inside that sphere. So let's say I'll put the translate to 1. So it's just sitting right there a little bit above the origin. Then inside here, for that emitter, let's go into wireframe mode. Obviously, we don't want it to emit particles in all directions. I want it to only emit particles up and then up and out. And so instead of using a omni emitter for that, I'm going to use a directional emitter. And a directional emitter by default is just going to emit particles going out in a line, like so. So I'm going to say, well, emit going in the Y direction, so it spits particles up. So now if I hit play, we're going to see that stream going up. But then I'm going to put a spread in there. Let's say a spread of about 0.9. So think of spread as being like a cone angle on a light. And so if I put the spread to 0, which is default, we get a line. If I put the spread to 1, it's like having a cone angle of 180 degrees. And so now you can see, all right, there you go. So you can see that already we're getting started with the idea of this ground explosion. But now what I need to do is obviously play with the rate on the emitter and animate it. And then also the speed. How fast are those particles coming out of that emitter? So first inside here, let's go and animate the rate. And so let's say at frame 1, the rate is, let's say, 500. And I'm going to keyframe that. But for my keys, I'm going to use stepped keyframes. And so basically, we're not going to have any interpolation between keys. And so if I choose stepped keys, and I'm changing my tangent types using a marking menu that I've created, the default way to do it is just go to your animation preferences by clicking down here. And then you can go in animation and change your in and out tangents. But instead of doing it that way, which takes some time, I prefer to just make a custom marking menu so I can change quickly. So I'll take my emitter and say, all right, well, at frame 1, your rate is 500. But then a few frames later, let's say around frame 10, the rate goes to 0. Let's key that and hit play. And now you can see what happens. I get this little burst coming out of that emitter. But obviously those particles are going a little slow. So now I want to take the speed on my emitter. Now, the speed attribute on an emitter just has to do with how fast the velocity of the emitted particles is going to be. Basically meaning that the emitter is going to contribute to the velocity attribute on the particles at birth. But always remember that the moment a particle is born, it's no longer related to the emitter anymore. So emitters don't act as accelerators. They don't continually tell the particle to keep going. They only at birth tell the particle what direction to move in. But at that point, the particle does what it wants to do based on fields. So if I go inside here and hit play and say, all right, well, I want to figure out what that speed should be. So let's say if I put a speed of 5, you'll see how they're going to move a lot faster. Speed of, let's say, 10. But with the speed that I have inside here, let's say I keep increasing it, because obviously something like an explosion, you're going to expect those particles to move pretty fast out of that emitter. But when you choose speed alone, without using speed random, all of the particles get the exact same velocity. And that's not something that I want, meaning I want some of the particles to move faster than other ones, so that we don't get this perfect dome of particles moving away from the emitter. And so that's where speed random becomes very useful. So I can say, well, the speed is 15, but let's randomize it, let's say, by 10. And now if you look at it, you can see a noticeable difference, meaning that if I hit play and then stop, it's not as much of a noticeable dome of particles as when the speed random was at 0. And if I hit play and stop, you can see it has more of a dome shape. So we'll use a speed random of 10 inside there. And so now you can see we're already getting a lot done. So with that done inside here, these particles, the debris particles, clearly need to also fall with gravity and then collide on the ground. And so to get them to fall with gravity, I just need to select them, go to Fields, and apply a gravity field. The gravity field by default is set to make things fall in the negative y direction. The default magnitude is 9.8. Since it's a field, it means it's an accelerator. It affects your particles every single frame, trying to get those particles to go faster and faster. And now if I hit play, we can see the default magnitude is actually okay. Usually it isn't. And so meaning that default of 9.8, usually you do not want to be thinking about reality, meaning that while in reality gravity affects things with an acceleration of 9.8 meters per second, that's fine for reality. But in Maya, it only makes sense if you're really working in world space units, which you usually aren't, and therefore just be aware magnitude. Well, right now, the default is okay. It usually needs to be tweaked, but we'll leave it alone for now. So I've got my little burst. Next thing I want to do is get those particles to collide with the ground plane. And so to do that, if I select the ground, since this ground plane is in here from before, it's already going to be set up to be able to collide with the particles. I'll see it does have a history node on it, which I don't need, so I'll just delete history on that ground plane. But if I go to the attribute editor for it and look inside here, it doesn't look like it actually has that geoconnector node on it. So let me look around and see if it does. It might have actually been deleted from earlier. But regardless, when you want particles to collide with a ground plane or any surface, you select the surface, go to Particles, Make Collide, and then in the options you specify your resilience, friction, and offset. So your resilience is how bouncy the surface is, and your friction is whether or not the surface, if a friction of 0, particles will slide right off the surface. Friction of 1, they'll stick. So we're going to want a little bit of bounciness, a little bit of friction. And then your offset is, do you want your particles to collide with the ground based on where the actual ground plane is, or collide with it a little bit before they touch the surface? Because for something like particle collisions, it always collides based on where the actual center of the particle is. So if you have, let's say, particles at the sphere mode, or you have instanced objects onto them, you might want to add a little bit of an offset. So for now, we'll just leave the offset as a default and hit Create. And then we'll see the geoconnector node when I select that plane. When the geoconnector node is selected, you'll see there's the resilience and the offset, but you'll also see a tessellation factor, which is how many polygons this object is tessellated into to determine your collision model. But for a ground plane, obviously the default is fine. So to connect the particles to collide with the ground, we have to go to the Dynamic Relationships editor, select our debris particles, go to Collisions, and click on the ground. And now, if I rewind and hit play, there we go. You can see that they move out, but you'll also notice that those definitely do have friction, meaning that they hit the ground but stop pretty quickly. You'll also notice that they do seem to be going through the ground, again because they are colliding based on the center of the particle. And then at this point, I could go and select my ground plane inside here. And for that ground plane, make some changes to the resilience and friction. So while this is playing, you can see that if I put the friction, let's say, to 0.2, they'll sort of slide a little further on the surface. If I put the resilience to 0.5, you'll see we get much more of a bounce. And so you have to think, even though this is resilience on the ground plane, it's really affecting the behavior of the particles. So do you want those particles to be bouncy like that? It's like, that's definitely a little too bouncy. So let's say resilience 0.2 or 0.3. And so that's giving us a little bit of a bounce, but that kind of works for what we're doing. And so something that's kind of heavy, like, let's say a rock or a piece of debris, will bounce, just not very high. It'll lose a lot of energy on its first bounce. So the effect that we're getting right now, as far as the amounts of bounciness, I think is working pretty well. I might lower that friction, or rather that resilience, just a tad. The friction that we have as far as how long it takes for these things to come to rest is okay. And at this point, we're good with that. Now, as far as if I wanted to play with that offset, let me go back to the attribute editor. If I put the offset, it's at 0.01. If I put it to 0.1, what you're going to find happen with that offset is while it does work, meaning you can see I can say offset 0.2, offset 0.3. So now it's starting to look more like those are sitting on the surface. You'll then also notice sort of a side effect of using offset is that they start doing these sort of extra bounces and never want to come to rest. And so that's something that you then have to counter with fields or expressions on the velocity of the particles. And so since we don't want to deal with that for this tutorial, I'll just leave the offset to 0.01. Because another way to deal with getting them to look like they're colliding with the ground and not going through it is to have two ground planes. One ground plane, which is the one that you see, that you render, and another invisible ground plane that's a little higher than the ground, which is invisible, doesn't render, it's transparent, and that's the one that is the actual collision model. So just to point you in a direction of how to approach something like that. So, but for now, we're also going to be fine with our behavior that we're getting for this tutorial. So the next thing now is like, okay, well, we've pretty much got our behavior down for our debris. So the next thing we want to do is we want to instance our rocks onto these particles. So I'm going to go and get my rocks to be visible. There they are. And let me go and let me select my camera and just see, okay, let's go and make a new camera to look through for this. Alrighty, so if I hit play and stop, I've got these 6 objects that I want to instance onto these particles. And so now is the time I'm going to take my particles and get them back into the default, which is point mode. So they're just these tiny points. And to get these instance onto my particles, the first thing is that even though they're all floating in the air right now, if I took these and moved them all to, let's say, 0, 0, 0, you'll see they'll all go to the origin. And that's important for the instancer to work, meaning that for objects you want to instance, 0, 0, 0 on their transform node needs to take them to the origin. And so if that's true, then you can put them anywhere you want and you can still instance them. Just make sure that you freeze transform objects at the origin so that you're going to be okay. And so let's say if I went inside here, like grab that one, put it at the origin, I can see that its scale has been tweaked from its original, so I could decide to freeze that too. I would just say freeze transform. And then I can go and put that up here. So if I took all of these and said 0, 0, 0, freeze transform, so they're all kind of defaulted out, then I grab these and move them all. They are ready to be instanced. And so the thing to do with instancing these objects, all right, is you select them all. And also, by the way, these objects do have simple shaders on them. So you can see that they just have simple blend shaders with rock textures assigned to them. Select these objects. So I'm just going to, let's say, select them in this order. So from left to right. And then in here, I'm going to go to Particles, Instancer. And in the options, with those objects selected, they show up in the object index list. And all of the defaults in here are fine. I do not need to change anything because all of the stuff down here that has to do with behavior, we're going to change on the particle node. And so there's no real reason to worry about assigning any of these attributes at this point. Also, since we are just wanting to randomize the placement of these 6 rocks onto my particles, the default options we have up here as far as cycling is fine, meaning I don't want to go in here and worry about any kind of cycling with my particles. And so if I go in here, I'm going to go and say reset, so we are at the default options, because you can see that cycle was set to sequential. And I don't want it to go and automatically animate through this list, because this list is not a sequence of animated objects. Meaning, for example, a bat flapping its wings, where each object represents a different state of the bat flapping its wings that the instancer would then cycle through. That's not what we're doing right now. And so going to the default options, it's not going to cycle. We're just going to have a list of 6 objects that are numbered 0 through 5, which is important to notice. So with everything at the defaults, down here you'll see it'll say particle object to instance, because you don't need to select the particle object when you use the instancer. You just select the objects, and then in here specify which particle object you want to instance these 6 objects onto. So my debris shape. Hit create, and you can see, there you go, that worked. So the only thing though that you will notice is that all of my particles are using this object because that's the first object in the list. And so now what we want to do is randomize so that my particles are randomly selecting from all 6 objects. And to do that, you have to go to your debris particle object, and you'll find that it has a whole bunch of attributes for the instancer. And so if I just go inside here, let's just quickly grab that shape node for my particle object. Whole bunch of folders inside here, but you just want to go to the instancer folder. And you'll see that there's all those things that we can map, one of which is object index. The object index we want to randomize. Basically, we want to write a creation expression that says the object index equals a random number between 0 and 5, right? Because these start at 0, 1, 2, 3, 4, 5. But when you click on this pop-up, what you get inside here are things that don't really make sense. The things it's giving you as options to map to object index are not what we want. And so this list is going to show your per particle attributes that you have on your particle shape node. So what I'm going to do is I'm going to add my own. I'm going to go and say add attribute. I'm going to make a custom per particle attribute. So this is going to be called my custom index for the object index list. And it's going to be a per particle attribute, meaning every single particle is going to get an attribute called custom index. And it's going to be a float, meaning that the number is going to be a 1.5 or 5.9 or negative 1.2. Those are what floats are. So they're single numbers with decimals, as opposed to a vector, which is something like color or position that has 3 components, like X, Y, Z, or RGB. So we want a float per particle array called custom index add. Then I can see custom index right there on my particle object. I right-click on it. I want to write a creation expression because I want custom index. I'm going to select it with the left mouse button, middle mouse button, drag it down here, and say it equals rand 0, 5, semicolon. And so create. So I've now written my expression for my attribute called custom index. Now this attribute doesn't do anything right now because it's not mapped to anything. It's just a per particle attribute storing a number. I want it to be a creation expression because I want at birth every single particle's custom index to be randomly assigned a number. But I don't want that number to change every frame, which is what would happen if I chose runtime. So, but also in here, something important to point out is that if I put rand 0, 5, and I know that my list of objects is numbered 0 through 5, the chances of us getting object 0 or 1 or 2 or 3 is going to be pretty good, but the chances of getting object ID 5 is going to be very small. Another thing to point out also is that rand 0, 5 spits out a float, while custom index is an integer, meaning custom index is a whole number, 0, 1, 2, 3, 4, while this is going to make a float. But you can do that in an expression. You can write an expression that is assigning a float to an integer. It's just going to ignore the decimal. So for example, if this spit out a value of 4.9, then what custom index is going to use is going to be 4, because it doesn't round up. You can think of it as rounding down, but it's not rounding. It's just ignoring the decimal. And so that's why the chances of getting object 5 are almost 0. And so what I can do in here is say rand 0, 5.9. Because if I put rand 0, 5.9, now there's a better chance of getting object 5 sometimes. Because if this spits out a number of 0.5, it's going to use 0. If it spits out a random number of 3.9, it's going to use object 3. And if it spits out a number of 5.2, it's going to use object 5. So I'm going to say that's what I want for my expression. Close it, go up here, and say on my instancer, I'm going to set the object index to equal custom index. And if I now rewind and hit play, you can see that it's randomly selecting from all of the objects. And so now it's starting to look a lot better. So I could go and switch to my regular camera view to sort of see how things are going. So that's starting to look a lot better. But then you'll notice once you use the instancer, I've still got these 6 objects floating up here. Well, you can just go and hide those. So I have those on a display layer, and so I'm just going to hide that display layer. And so inside here, let's also hit 7 to turn on lighting so we can actually still see our little flash. So we can see that things are sort of coming along inside here. If I go and do a render at this point, let's open the render view window. And so, don't need that image inside here. So let's save that. Let's do another render. And you can see things are working fine inside here. You can see that my debris is in there, that it is casting shadows. I don't have motion blur on inside here, but that's something I could turn on. At this point, what might we want to do? Well, if we go and switch through to our other camera, you'll see inside here that whenever I hit play, that those pieces of debris, when we look at these 4, we can see those are definitely the same object being instanced. So the fact that it's not rotating randomly these objects or randomly scaling them, or maybe getting these things to spin as they're flying through the air, which might be a little more natural, because you notice that these things are moving, but they have absolutely no rotation at all. So the next thing we might want to do is, how do we randomize scale? How do we randomize rotation? How do we get them to spin around? How do we get them to spin around so they're spinning, but once they hit the ground, they sort of stop spinning so much, and then once the particles come to rest, they don't spin at all. All of that kind of stuff. Now, you're not going to get these pieces of debris to collide and bounce accurately on the ground based on the geometry, because for that you'd use rigid body dynamics. When you do instancing for debris, you're doing it for the small pieces of debris, where nobody would ever notice that they're not actually colliding accurately. It just has to look good enough. For large chunks of debris that are near camera, then for those you just would use rigid body dynamics, so they do bounce around based on the geometry. But for this, you're trying to sort of get it to look good without worrying about it being 100% accurate, because we know that from the camera perspective we're rendering from, nobody would really ever notice. But if I go back to this camera, how about randomizing the scale and the rotation? So let's do that next. So to randomize the scale on these things, I'm just going to go to my particle object and go back to the instancer folder. And inside here we'll see that we have scale and we have rotation. But again, if I go to, let's say, to scale and click inside here, nothing in here really makes sense to map to scale. I don't want the scale to change based on their acceleration or based on their position. So what I'm going to do inside here is, again, create a custom attribute to assign to scale. So I'm going to add an attribute called my custom scale. Now, scale is a vector. And so if I go and say, well, I want to randomize the scale and have control over the X, Y, and Z scale attributes, then I would want to choose a vector for scale. Because obviously, since I'm mapping this to something that is a vector, making it a vector is going to work. But you could make it a float if you wanted to. Because if I make scale a float attribute, so it's only a single digit, and I assign that to my scale vector, the vector is going to use that float number in all 3 spots, X, Y, and Z. So if you want to do proportional scaling, meaning that it's going to scale the same in X, Y, and Z, you could just go and make scale a float. But if you want to do non-proportional scaling, so that it might scale differently in X than Y than Z and randomize in all 3 axes, then you would want to make it a vector. And so let's go in here and just make it a vector. Per particle, add. Let's now go and write a creation expression. So there's custom scale, right click, creation expression, new line, custom scale. What do I want that to equal? Well, it's a vector, which means we have to use this syntax where in our angled brackets I can say custom scale equals. Well, the scale right now basically has a value that's based on the default scale that the objects had. So let's just go in here and say, well, what if I did custom scale equals 1, 1, 1? That would just mean scale of X 1, scale of Y 1, scale of Z 1. And I have that be my expression. And I go up here and I go to scale and I say, let's map that custom scale. Then let's rewind and hit play. Now you can see that they're all just basically at the sizes that they were at before. But now we have that attribute working, meaning that we're defining scale having a value of 1 and then mapping it up here to scale. So I'm going to go down here and say, all right, well, let's go to our expression and now change it. Let's say we want to randomize it. Well, if I want to randomize it proportionally, I could go inside here and say, well, I could go and just put a single number inside here. Let's say like a random number. But if I really want to make sure I'm doing proportional scaling, the way I would like to do it is do something like this. Float rand scale equals rand, let's say 0.2 comma 1. And then down here, I would go and take rand scale and paste it inside here. Rand scale, rand scale, rand scale. So I've just defined a variable. So I defined a float variable called rand scale. So I'm saying it's going to be a float, $rand scale to specify what it's called, assigning it a value. But this is creation, so it only gets assigned once, a random number between 0.2 and 1. So basically I'm going to get some smaller debris inside here. So I could say, well, maybe 0.2 is a little too small. So let's say 0.4, comma 1. And then for my custom scale, I'm saying, well, that equals, and if I do this, rand scale for X, rand scale for Y, rand scale for Z, they're all going to get the same exact number, and it'll proportionally scale. Because if I went and did something like this, let's say I grab that, copy, and put that inside here, paste, comma, paste, comma, paste, this will not give me the same result, because this is going to calculate 3 times. So X might get 0.5, and Y might get 0.6, and Z might get 0.4, and it won't proportionally scale. So even though it's the same range, it's still going to calculate a different random number 3 times. So that's why inside here, this is going to give us proportional scaling. So let's go and say, all right, well, let's enter that inside there, rewind and play. And now you can see I've got some tiny ones, and I've got some bigger ones. And so I could just go back to my render cam just to see, well, is that okay? And that actually looks fine for what we're doing. So I've got some bigger ones and some smaller ones. So now the other thing inside here, now we're pretty much got that going on, is the rotation. So let's go through this cam, and let's go and add some rotation inside here. But before we do that, let's go inside here and let's save this. So where should we save it to? I guess I'll just save it inside here. And let's go up a level and just go and say where this is going to be Gnomonology. And inside here, I'll just call it ground explosion. Always good to save. Never know when something could crash, because Maya does like to do that sometimes. And let's go in and be like, all right, rotation. We've randomized scale, now we want to randomize rotation. So we go to the particle object. We now need to go up here and map rotation. So, of course, in here, nothing in here makes any sense as far as what we want to use. So, add attribute. This is my custom rotation. This is a vector per particle array. Add. And then let's go write a creation expression. So at birth, the first thing I want to do is randomize the rotation so that they are not all oriented exactly the same way. So that when I see the same piece of debris, like that one and that one and that one, we can kind of really tell that the same object is in there 5, 6 times. Well, we don't want people to be able to tell that we only have 6 source objects. And so the way that you sort of hide that is by randomizing as many attributes as possible. Same thing is true if you're doing sprite rendering with particles. So I'm going to go inside here and be like, all right, well, custom rotation equals, and for this, let's do this, rand 360, comma, rand 360, comma, rand 360. So rand is something that usually expects a minimum and a maximum. If you just put a single number in there, it's going to assume the minimum is 0. So rand 360 is the same thing as typing rand 0, comma 360. So I'm just going to do that, shorthand. And like I was talking about with custom scale I wanted it to be proportional. But custom rotation, I actually want a different number for X, Y, and Z. So by saying I want to randomize rotate X, rotate Y, rotate Z, from 0 to 360 degrees, I can now say, and that again is creation, so it's going to create a random rotation vector for each one of my particles at birth. And then go up here, go to rotation, and map that to my custom rotation. And then rewind, play. And it'll now get sort of harder to spot the same instanced object. You will be able to see it, but you'll notice it's now looks much more random, much more organic. Because when we look and try and find the same rock, we can basically say, well, you know, that one and that one are probably the same one, maybe. You know, and so it really helps. Like this one and this one are probably the same one. But that random rotation really, really helps inside here. Now, the only thing to point out when I hit play, though, is, okay, well, we've now randomized scale and we've randomized rotation. But what about getting them to spin? Because you can see they're still all static in the air as they float in the air. If you sort of just watch one of them, you'll see that it doesn't spin around. So to add a little bit of spin, that's again going to be rotation, but instead of creation, we want it to be runtime. And so if I go inside here to my expression on rotation, this is all under creation. But now I'm going to edit my rotation using a runtime expression so that the rotation can actually change over time. Now, for runtime, we have before dynamics and after dynamics. For what we're doing right now, it doesn't make a difference. Meaning, is it going to calculate this expression before things like fields? Because fields contribute to acceleration on your particles. So if you're writing an expression that also affects the acceleration on your particles, it'll make a difference whether the expression is calculated before fields or after fields. And so since what we're doing right now is just the rotation on the instancer, it makes no difference. So we'll just leave it at before dynamics. And we'll say custom rotation. Well, how do we get that to change so that our particles spin around? Well, a very easy thing to do is be like, well, I know that I assigned a random rotation at birth. So what I want them to do is take the random rotation they have at birth and then go from there. So the best way to do that is to basically say the custom rotation equals custom rotation, let's say +1. If you did that, this means take the value you already have and then add 1 to it every single frame. And shorthand for that is this, plus equals. So if I write plus equals, then it's going to take the value it already has and then add 1 to it. So I can say, you know, times equals, minus equals, plus equals. So inside here, if I go and do something like that and say plus equals 1, that's going to be a really big value, and that's going to make them spin around like crazy. But let's just go and see what happens if we do that. So let's say create, rewind, play. And now you'll see that those things are spinning. So that's not actually so crazy. But you can see it's working. It definitely is getting our particles to have a little bit of spin to it, and it's actually looking pretty nice. The only thing is that they continue to spin when they hit the ground, which we're going to have to deal with. But when they're in the air, we have something that works. So let's go up here. So how do we go and get it so that they don't actually continue to spin when they hit the ground? And also the fact that they're all spinning like the same exact amount. Like some aren't spinning faster than other ones. So the way that we could go and do that is there's a couple things we could do. One is we could make sort of like a random rotation attribute that's added to each one of our particles so that they don't all spin the same amount. But if we want them to spin at different rates, but one particle spinning fast for its lifespan and another particle spinning slow for its lifespan, we'd have to set some sort of new attribute that has to do with the rate of spin and define that at creation so that particles get something that's assigned at creation as a single value and then used for their whole lifespan. And so that would mean creating another new attribute. Let's say something that's sort of like randomizing the rotation. So let's say we want a rand rotation, which inside here would be a float per particle attribute, which I can define in a creation. So let's say rand rotation inside here Let's just put some spaces inside here so it's easier to read what we're doing. Rand rotation equals, let's say, a random number. Let's say we did -1, 1. Then every single particle at birth is getting a random number between -1 and 1. Then in my runtime expression, I could use that inside here. I could say custom rotation plus equals rand rotation. And if I do that, it then means that basically it's at birth going to assign a number from -1 to 1, rand rotation. Every particle has a rand rotation attribute now. Then this number, -1 to 1, is used in the runtime. And so for some of my particles, they're going to get a plus equals 0.5. Some of them are going to get a plus equals -0.2. And if you do plus equals with a negative number, it'll subtract. So this now, if I go and rewind and play, is going to again get some of these particles to spin faster than others. So basically it's working. So if I want to have it be a little bit more noticeable, I could say, -5, 5, edit, rewind, play, and then it'll be more and more noticeable that some are spinning fast and some are spinning slow. Just sort of watch how they're spinning on the ground. You can see that one's going really fast, while some of them are going very, very slowly. So the sort of amount, let's sort of close this out so you can see that a little better. The amount of randomization that you want and the rate at which these things are tumbling around or spinning, you have control over, is my point. And so again, we just have to go out here, edit our expression, and say, well, that's maybe too much. Let's say 0.2, 2. Edit that. Go to our runtime. And at this point, we're pretty much good except for the fact that what about getting them to stop spinning when they're on the ground? Well, to do that, what I want to do is utilize their velocity. Have a way to have their speed affect whether or not they're rotating. So that if their speed equals 0, this would basically be able to say, if I had something like time speed and speed was 0, then they would stop spinning. But the thing is, I don't have an attribute yet called speed. I need to add that. Your particles do have an attribute called velocity, but that's a vector. That's an XYZ vector. So what we need to do is figure out how do we get speed or derive speed from velocity. And that's done. I'm going to go back to my runtime expression by doing this. I'm going to define it. Float speed equals the magnitude of velocity. And there you go. We have now defined speed. Speed equals the magnitude of velocity. Magnitude is a function that does the square root of x squared plus y squared plus z squared. So if velocity equaled 0, 10, 0, meaning it's going up in y with a value of 10 units per second, then the square root of x squared plus y squared plus z squared would be the square root of 100, which would equal 10. And so if this was 0, 10, 0, this would equal 10. So MAGA velocity is a very useful thing to remember because it does give you speed. And so if I say float $sign speed, meaning define a variable that's a float called speed, I now can use it for something. For example, I could go in here and say equals that times speed. And that is going to be able to get me to control what's going on inside here. But there's a very important thing to point out right now is that my speed attribute is not normalized. It doesn't go from 0 to 1. It goes from 0 to I have no idea what at this point. So while we have defined it, it's not necessarily going to work well what we have going on inside here unless we could somehow normalize speed so that we know that a value of 0 means it's not moving and a value of 1 means that it's moving at its maximum speed. So normalizing an attribute is a process of basically dividing it by its maximum value. So if you have something that goes from 0 to 50 and you divide it by 50, it now goes from 0 to 1. So in order to keep the behavior that we already had in here, but just get it to slow down when the particle slows down, we really need this to be normalized speed, meaning that it just goes from 0 to 1. And so while this does give us speed, what we really want is to have something that is, normalized speed. And to normalize it, you basically need to take mag velocity divided by max speed. But where does max speed come from? And max speed is something you got to figure out. And the way that we figure that out, let's close all this, is we need to be able to look at our particles and see the speed attribute. But we can't see the speed on our particles, like how fast they're moving, when you're using a defined variable. Meaning if I go in here and say float, again, $sign speed equals the mag of velocity, I can't go in and see what speed is. So instead of defining speed as a variable, we're not going to do that. We're going to actually define speed as a new attribute, so that every particle has a float per particle attribute called speed, so that it gets added here. So it's not a variable, it's a new per particle attribute. Because then I can write an expression that's defining speed, but not as a variable, equals the mag of velocity, edit. So now, debris shape dot speed equals the mag of velocity. So now that I've defined it as a variable, and it has to be runtime, because speed changes every frame, right? So it's not a creation, it's a runtime defining what speed is. I'm still not using it down here yet, though. But now I've defined speed. So now what I can do is something cool, which is to figure out the max speed of your particles. I'm going to take my instancer that's inside here, and I'm going to hide it for a second, visibility off. Then I'm going to take my debris particles that are right now in point mode. Let's go and take that. Go to the render attributes and change them to numeric. Numeric mode is going to show you the particle ID for all of the particles, but I don't want to see particle ID. I want to add attributes for numeric and change the attribute name to speed. So it's showing me the speed attribute. So any per particle attribute you have down here can be displayed. And so if I display speed, something that I've already created and I've defined with my runtime expression, I can now look inside here and see the speed of my particles. And as that's playing, the first period you're seeing there is your particle. That's not a decimal. So this particle is moving at 9.967 units per second. So what I basically need to do is hit play, stop, and look for the biggest number, because that tells me what the max speed is. And while this may seem a little like, well, that's kind of a weird way to figure out your max speed by just looking around for a big number, it's the most efficient way to do it, because this way your expression will calculate very quickly once you figure out your max speed. Because otherwise you'd have to have an expression that evaluated every single particle at every single frame of the entire simulation to figure out the fastest the particles ever moving. This way it's just simpler. So I can see, all right, well, there's an 18, there's a 19. So do I see anything around here that looks like a 20? And I don't. And so 19 seems to be the fastest. Let's rewind, play, stop. Maybe at the beginning it's going faster. It's like, nah, doesn't seem to be. So it still looks like 19 is the fastest. Play, stop. 19, I see a 19. Looking around, don't see anything bigger than that. Play, stop. Looking for a bigger number. So since 19 seems to be the biggest number that I saw inside here, and obviously it's just going to go down and down and down. Since 19 is the biggest number, I could just use a value of 30, right? So just using something a lot bigger than what I saw, and I know I'm safe. So let's go back to point mode, turn our instancer back on, visibility, go back to the particle object, go back to speed, go back to my runtime, and say speed equals the mag of debris shape dot velocity divided by 30. And I have now normalized it, meaning it's now definitely in a 0 to 1 range. And so if I now hit edit, close, go back to numeric mode, you'll see inside here, if I rewind and play, that all of them are now between 0 and 1. So you can see 0.2, 0.3, and so forth. And so since that's definitely true, I can also see inside here that when they come to rest on the ground, they're not actually truly coming to rest. There are these tiny baby bounces going on, another thing we're going to have to get rid of. But basically you can see the numbers are going down. So now what we want to do is get this speed to affect our rotation, and then we can get into getting these to stop moving when they're on the ground. And so let's move on to that next. As far as the rotation, let's take our particles and say, all right, you're back in point mode. And now we want the rotation to slow down so they stop spinning when they hit the ground and stop moving. So I go to my runtime and say rand rotation, or custom rotation, plus equals the rand rotation times speed. And so now if I rewind and play, they'll rotate based on them spinning, but then they'll stop rotating once the particle slows down. So you can see none of them are rotating on the ground anymore. They still have those tiny little bounces we have to get rid of, but you can see that when they're in the air, there's a little bit of a spin on them. Although I need to sort of make that a little bit more noticeable because this is a small number. So my rand rotation, I'm going to say maybe is negative 5,5. Edit. So rewind, play. I can look at them and see they're definitely spinning, but they also definitely stop spinning when they hit the ground. So I'll let this play a few times so you can see it's working. So when they're in the air, they are spinning. They have a little bit of rotation and orientation that then goes away when they hit the ground. And if I want it to be even more noticeable, all I have to do is go to my expression for rand rotation and say let's make it twice as fast as far as how much they're spinning. But then they do definitely come to rest and stop spinning on the ground. All right, so now next thing, let's get rid of those little baby bounces that we have when they hit the ground. And before we do that, let's just rewind and save our progress. All right, so to get rid of these small bounces, which are not as noticeable when we look at it like this, but if I grab the particle object, get it into numeric mode, so we see the speed, and hide the instancer, visibility 0. We can now see, when I rewind and play, that because of just a quirky behavior of particle collisions, they really don't like to come completely to rest. And while that can be annoying, it's simple to modify by writing an expression on the velocity of your particles, just saying if the velocity gets, let's say, below 0.01, that it just equals 0. So you force it to be 0. And that would be the kind of runtime expression you would want to calculate after dynamics, meaning after it's figured out the velocity as a result of collisions, you then are overriding that with an expression that's calculated after dynamics. And so to do something like that, since we want to do it based on speed, we're going to go to our, because that's what we're looking at here, and so 0.01, let's just go and see if that's actually true. Everything in here looks like it's less than 0.01 if we look around inside here. And so that seems like less than 0.01 will probably work. We will then go in here to our particles and write an expression on velocity. And so right now velocity has a little something in there because we used it to define speed. So it's used in an expression, so that's why it's got that there. But we're going to now, if we go to our expressions, we can see here's our creation expressions, runtime before dynamics, where we're defining speed using velocity. But now we're going to do a runtime after dynamics on velocity. But this is going to be a conditional expression, basically saying if speed is less than 0.01, velocity equals 0. And so if speed, which is the mag of velocity, right, but we want it to be the speed that we normalized, the one we're looking at here. So that's divided by 30. So all of that needs to be in parentheses. So if the mag of velocity divided by 30 is less than 0.01, velocity equals 0. So that's a conditional expression. So if the normalized speed is less than 0.01, velocity is forced to be 0, not these tiny little numbers we're getting. And so I'm going to create that. Let's just go and make all this smaller. Create, rewind, play. And you'll see when it plays, they all end up at 0. And if we look around, we can see it actually looks like there's one in here that's not zeroing out. This little guy right there. And so let's stop. And we can see, there you go. It's not less than 0.01. It's actually wanting to be 0.014. So here I'll say less than 0.02. Edit that expression, and that got forced to 0. So now, if I close all this and hit play, everything's fine, everything's normal, but then finally they do all come to rest, as we can see inside here. And so since they all come to rest, and in here you can see that that's leaving some particles up high because they sort of slowed down up there. Then we need to sort of deal with what are we going to do about those. And so for those, what I can do is edit my expression, runtime after dynamics, and say, okay, well, I don't want it to force them to go to 0 if they're up in the air. And so you can see that when it was 0.01, and we played it, those were still able to hit the ground. But 0.02 was too high. Now I could go say 0.015 and maybe get lucky and have that work, but you can see it doesn't. So what I'm going to do is say if the mag of velocity divided by 30, the normalized speed, is less than 0.2 inside here, and I want to specify that if the height in y is less than 1, so meaning 1 unit, so I know that they're down low, I want to be able to control it. So how do I figure out or query the y position of these particles? And to do that, I know that my particles have a position attribute, but the thing is I can't go and write, position dot y. Even though the position is a vector, if you want to query one of the individual components in a vector, you can't just write it like that. So what you need to do is you need to actually assign it vector position equals position. And so I'm taking my position vector and turning it into a variable vector. So defining a vector called $position. And so again, this is the particle position, right? So let's say we call it, particle position. And with this also, when you're dealing with position, to make sure you're working in world space, you might actually want to use world position, because particles actually have two position vectors. They have position and world position. You can see that in this list of attributes on our particle object. And since particles are able to exist in local space as well as world space, I'm going to make sure that this position attribute that I'm using inside here is in world space. So I'm defining a vector variable called particle position, which equals world position. And then inside here, I can say if the velocity is less than 0.2 and particle position dot y is less than 1. And then all of this stuff needs to be in parentheses. And so now basically I've defined a vector that's also runtime, meaning that it calculates itself every single frame. It's called particle position, and since it's a variable, you're allowed to put .y at the end to specify the y component. So this maybe, if you haven't done this kind of stuff, may look a little strange, but it's relatively straightforward. So we've defined a variable, and we're querying the y component of that vector. And so now if I edit and rewind and hit play, they're able to fall back down. So now if we look inside here, we'll see that they all come to rest, and none of them stay floating in the air. So it's definitely one of those kind of Maya dynamics things. Just like, wow, does it really need to be so hard? But that's just the way Maya dynamics are. And so it's something that once you get used to, it's really not that bad. And you can see I was able to get everything to come to rest. And then I have this one particle there. You can see that kind of falls down slowly. And for that one, I could just say, well, runtime after dynamics, instead of less than 1, let's say less than 0.5 in y. Because I know my ground plane is at 0. And so if I now go inside here and hit play, we'll see that those particles are fine. So I could have it be less than 0.1 or whatever. We don't need to get too anal. So now, with all of that done, I can take my particles, get them to be in point mode again, take my instancer, get that to be visible, and now when I go inside here and hit play, let's go through the perspective view, and let's select that so that we can see it. Let's actually select the instancer node. And now when I hit play, we can see that now after all of that time, we've got our debris, we've got the debris that's flying out. We can see that when it's in the air, they're rotating. And so if you just sort of follow individual ones, you can see there's definitely spin and rotation that's randomized on our pieces of debris. But we also can see that when they hit the ground, they stop rotating slowly, so they come to rest. And then when they come to rest, they really are at rest. There's no little tiny baby bounces in there at all. And so now we are done with our debris. And so the next step is how do we get our particles to emit particles to get the smoke trails. So we are now done with the instancer part of this tutorial, and we'll move on to the software rendering cloud particles part where we do the smoke trails. And so let's go and do that next. So I'm just going to rewind to frame 1 and save my scene. I'm rewinding to frame 1 because the file size will be smaller, because if I hit play and save it like this, it's going to be, saving the scene with all the particles in there. So just to save disk space, it's a good idea to rewind to frame 1 before you have a lot of particles in your scene. Save it, and it'll just be a little smaller. So let's now move on to the smoke trails.